Okay, let's wrap up our analysis of competition models by now taking a look at the behavior of a second model. The only difference between this second model and the first model that we studied in depth in the other video is that the parameters have changed just a little bit. Actually, the carrying capacity stayed the same, but what happened here was these numbers changed, like where there's a 2 here, there used to be a 1 there, where there was a 0.5 there, that changed to a -1 there. And that little bit of change actually results in a whole world of change as we analyze the phase plane or the state space of the system. I'm not going to go through in detail how I got this. It's pretty much the same way that I got that. But I want to draw your attention to some very important defining differences between the two models. The thing I want you to really pay attention to is that in this model that we analyzed in the other video, the blue line that was sloping downwards was above the red line in this region here, and then the red line is above the blue line for this region over here. Now, when you compare that directly with the phase plane for the other model, you're going to see that the red line is on top of the blue line at first. See how it's different in this one? Blue line on top, red line on bottom. Red line on top, blue line on bottom. And then over here, after we moved past the coexisting fixed point, this one had red on top, blue on bottom. This one has blue on top, red on bottom. So at first glance, you might think that's not really a big deal. But when you start to overlay the components of the vector field, and that reveals the stability of the various fixed points, you see that before, where we had the two species individually existing and the other one going extinct, those were saddle points before. So those weren't really going to happen. What's going to happen is no matter where you start, trajectories are going to be attracted to this attractor of the stable fixed point. Over here in this situation, it's entirely changed. Now, the fixed point that communicates coexistence of the species is now a saddle point. So it has a little bit of behavior where things are attracted, but it also has a dimension where things are repelled from it. And what happens is that repelling behavior pushes the systems towards the now stable fixed points down here that predicts just deer with no moose, and up here that just predicts just moose with no deer. And so what's going to happen in this type of model is, depending on what your initial condition is, either if you start over here, you'll be funneled toward just deer, or if you start over here, you're going to be funneled up here towards just moose. Even if you start kind of close to the saddle point, the problem with saddle points is that they're generally unstable. So even if you start nearby it, it's going to be repelled away from it because it has at least one dimension of repelling behavior, and then it's going to get funneled into this stable fixed point or that stable fixed point depending on where you're starting. So it's really amazing that this model can predict so many different things. It can either predict a happy coexistence of two competing species, or a deathly battle for the win, where either one will survive or the other will survive. And it all depends on your understanding of the nullclines, because really, I'll get out of the way so you can see the beauty. Really, underneath it all, the stability of the fixed points just depends on how the nullclines are intersecting each other. Amazing. So glad I know nullclines.